Hey everyone, and welcome back. I'm so excited to be diving deep into work and energy today. It's a topic that seems simple at first glance, but trust me, it gets really fascinating the more you explore it. We always say here that we want to uncover the stuff that makes you see the world differently. Well, this deep dive is exactly that. And to help us through all the physics and really break it down in a way that anyone can understand, I've got a fantastic expert with us.
Hello, everyone. I'm excited to be here.
So let's just jump right in. We're talking about work and Energy Bite. Like I said, it's way more interesting than it might seem at first. To start things off, maybe we can tackle work first. I know it's something we all use in our daily language, like, I'm working on this project or I got to work out. But I have a feeling the physics definition of work is going to be a bit different.
Yeah, you're absolutely right. When we talk about work in physics, we're talking about something very specific. It's not just about effort or exertion like we might think of in everyday life.
Okay, so what does it actually mean then? What's the physics version of work?
Imagine you're pushing a shopping cart down the aisle at the grocery store. You're putting in effort to keep it moving right. But believe it or not, from a physics perspective, you're not actually doing any work on the cart while it's moving at that steady speed.
Huh, really? But I'm definitely putting in effort. What's the catch here?
The key is in how physics defines work. For work to be done in the physics sense, there needs to be a force applied to an object. And that force needs to cause a displacement in the direction of the force.
Okay, I think I'm following so far.
So in the case of the shopping cart, you're applying a force to keep it moving. But that force is mainly counteracting friction. It's not causing the cart to speed up or change direction significantly.
So the force and the movement have to be working together, right?
Exactly.
So if I'm getting this right, if I lift a heavy box off the floor, I'm doing work because I'm applying an upward force and the box is moving upwards. But if I'm just holding that box steady, even though it's heavy, I'm not actually doing any work in the physics sense.
That's exactly right, because there's no displacement. The box isn't moving up or down while you're just holding it.
Mind-blowing. So could we maybe lay down the official physics definition of work just so we're all on the same page?
Absolutely. Work in physics is defined as the product of the force applied to an object and the displacement of the object in the direction of the force. You can think of it as work equals force times displacement.
Got it. Work equals force times displacement. But wait, there's more, right? Didn't you mention something about positive and negative work?
Oh, you have a sharp memory. Yes, you're absolutely right. Work can be positive or negative, and it all depends on the direction of the force and the displacement.
Okay, now you have to explain this to me because I'm a bit lost.
No worries. It's actually pretty intuitive once you get the hang of it. If the force and the displacement are in the same direction, the work is positive. Like when you lift that box up, you're applying an upward force and the box is moving upwards, so that's positive work.
Makes sense.
But if the force and displacement are in opposite directions, the work is negative. So imagine you're lowering that same box back down to the floor. You're still applying an upward force to control its descent. But the box is moving downward.
Oh, I see what you mean.
In this case, you're doing negative work.
It's like I'm fighting against gravity a little bit, right?
Exactly. Gravity is doing positive work as it pulls the box down, and you're doing negative work to control that descent.
This is really making me rethink how I use the word work. But I get it. Now work is about force and displacement, and they got to be in the same direction for it to be positive work. I guess we could say negative work is when they're kind of working against each other.
Yeah, that's a great way to think about it.
This is so cool. I never thought about work in such a precise way. But you know what I'm thinking? This precise definition is going to be super important as we dive deeper into energy. Because aren't work and energy super closely related?
You're absolutely right. They're practically inseparable. Energy is essentially the capacity to do work.
So all those different types of energy we hear about, like kinetic energy and potential energy, they all have something to do with the ability to do work.
Exactly. Each form of energy has the potential to create a force that can cause displacement and therefore do work.
Wow, this is getting me excited to learn more about all the different types of energy. But I guess that'll have to wait for part 2 of this deep dive. For now, let's just take a moment to really appreciate how this clear understanding of work is setting us up to unlock a whole world of energy knowledge.
I completely agree, and I can't wait to explore it with you all.
Me too. This is going to be epic. All right, we're back and ready to dive into the world of energy. Last time we really got a handle on work in the physics sense, force and displacement and all that. But now it's time to tackle energy itself. And I'm particularly interested in kinetic energy because it's the energy of motion. And motion is, like, everywhere, right?
It is. Everything around us is in motion in some way, even if we can't see it with the naked eye.
Mm.
From the tiniest particles to the planets and galaxies, everything's moving.
So that means everything has kinetic energy.
Exactly. If something is moving, it possesses kinetic energy.
Okay, so give us some real-world examples.
Sure, think about a speeding car, a rolling ball, a spinning top, or even the wind.
I'm starting to get the picture. So the faster something is moving, the more kinetic energy it has.
Absolutely. And it's not just about speed. Mass also plays a role. Think about a bowling ball rolling down the lane compared to a tennis ball rolling at the same speed. The bowling ball, with its greater mass, is going to pack a much bigger punch because it has more kinetic energy.
That makes sense. I guess it's kind of intuitive. A bowling ball definitely has more energy than a tennis ball, even if they're moving at the same speed.
Yeah.
But is there a way to actually calculate kinetic energy, like put a number on it?
There is. Kinetic energy is equal to 1/2 of an object's mass multiplied by its velocity squared.
Okay, hold on. Let me write that down. Kinetic energy equals 1/2 times mass times velocity squared.
Got it.
All right, starting to see the implications here. If velocity is squared, that means even a small increase in speed can significantly increase kinetic energy.
Exactly. And that's why things like speeding cars can be so dangerous.
Right, because even if you only increase your speed a little bit, the kinetic energy of your car increases by a lot. And that means more potential for damage if something goes wrong.
Exactly. Kinetic energy is a powerful force, and it's important to understand how it works so we can stay safe.
Totally agreed. Well, now that we've covered the energy of motion, what about the energy of things that aren't moving? Is there energy even in stillness?
That's a great question, and it leads us to another fascinating type of energy, potential energy.
Potential energy. Okay, I'm intrigued.
Potential energy is the energy an object possesses due to its position or configuration.
So it's like energy that's stored up and waiting to be released.
Exactly. Think about a book perched high on a shelf. It's not moving, so it has no kinetic energy. But because of its position relative to the ground, it has stored energy, gravitational potential energy.
So if that book were to fall off the shelf, that potential energy would be converted into kinetic energy.
Precisely. As the book falls, it loses potential energy, but gains kinetic energy.
It's like a trade-off. And the higher the shelf, the more potential energy the book has to begin with.
Exactly. The greater the height, the greater the potential energy.
This reminds me of roller coasters. They slowly climb that first hill, building up all this potential energy. And then when they plunge down, all that stored energy transforms into kinetic energy, making the ride so thrilling.
You got it. Roller coasters are a great example of energy transformations. And here's another mind-blowing fact. The total energy of the universe is believed to be constant. It's never created or destroyed, just transformed from one form to another.
Whoa, that's heavy. So the energy that powered the dinosaurs is still around today, just in different forms.
Absolutely. It might be stored in fossil fuels, or it could have been transformed into heat, light, or other forms of energy.
That's incredible. So there's this constant dance of energy transformations happening all around us. We've covered work kinetic energy and potential energy so far. Is there anything else on the energy menu?
There's a whole feast of energy forms out there. We've got thermal energy, chemical energy, electrical energy, light energy, and more.
I'm getting hungry for more energy knowledge. Can you give us a quick rundown of some of these other types?
Sure. Think about a light bulb. Electrical energy flows through the filament and transforms into light and heat.
Ah, so that's how we get light from electricity. It's an energy transformation.
You got it.
And what about heat? Is heat a form of energy too?
Absolutely. Heat is related to the kinetic energy of the atoms and molecules within a substance. The hotter the substance, the faster those particles are moving and the more kinetic energy they have.
So even heat is connected to motion at a really tiny level.
You're seeing the connections. And speaking of connections, what about the energy stored in the food we eat?
Yeah, that's chemical energy, right?
Exactly. Chemical energy is stored in the bonds between atoms and molecules. When we eat food, our bodies break down those bonds, releasing that stored energy to fuel our activities.
Wow. I never thought about eating as a form of energy transfer. This is making me see the world in a whole new light.
We've talked about work and all sorts of energy now, but I haven't heard you mention power. Isn't power related to energy too? It is. Power and energy are definitely related, but they're not quite the same thing. Power is the rate at which work is done, or the rate at which energy is transferred.
So power is about how quickly work is done or energy is used.
Exactly. Let's say you and I both carry the same heavy box up a flight of stairs. We both do the same amount of work because we're applying the same force over the same distance. But if I reach the top of the stairs faster than you, I've exerted more power.
because you did the same work in less time.
Exactly.
I guess that's why we talk about powerful engines and powerful athletes.
It's all about how quickly they can generate and use energy.
Okay, so power is the rate of energy use or work done.
You're getting it.
This is all so fascinating, but I gotta admit, it's a lot to take in. Maybe we should do a quick recap just to make sure everyone's following along.
Great idea. So we started with kinetic energy, the energy of motion. Then we moved on to potential energy, the energy of position. And we talked about how energy is never created or destroyed, only transformed. And finally, we touched on power, which is how quickly energy is used or work is done.
I think I'm starting to see how all these pieces fit together. It's like we're building a foundation for understanding how the universe works at a fundamental level.
I love that analogy. We're laying the groundwork for a deeper understanding of everything around us.
And I can't wait to see what we build on this foundation. Stay tuned for part 3, where we'll explore even more amazing energy insights. Wow, I'm still processing all that amazing stuff about energy transformations and, the law of conservation of energy.
Yeah, it's pretty mind-blowing when you really start to think about it.
Definitely. It makes you realize just how connected everything is. But before we totally wrap up this deep dive, I kind of want to bring things back down to earth a bit. Like, how does all this knowledge about work and energy actually apply to our daily lives?
That's a great point. It's not just theoretical.
So how can we use this to be more efficient or, make better choices about how we use energy in our everyday routines?
We'll think back to our example of carrying that heavy grocery bag. You're not doing work on the bag in the physics sense if you're walking at a constant speed.
Right, because there's no displacement.
Exactly. But you're still using energy. Your muscles are working to keep that bag moving.
So even if it's not work in the physics sense, it's still work for my body.
Yeah. And that energy has to come from somewhere, right?
From the food I eat, I guess.
Exactly. That's chemical energy stored in the food being converted into mechanical energy to power your muscles.
So even simple things like carrying groceries involve energy transformations.
It's happening all the time. And realizing that can help us be more mindful of our energy use, even in everyday activities.
I see what you mean. It's like realizing how much energy goes into everything we do. This makes me think about exercise, too. Like if I'm lifting weights, I'm definitely doing work in the physics sense, right?
Absolutely. You're applying a force to lift the weights and they're moving upwards, so that's work.
Yeah.
And the more weight you lift or the more repetitions you do, the more work you're doing and the more energy you're using.
So working out is literally work. No wonder it makes you tired.
And speaking of getting tired, our homes use a ton of energy, too. Understanding power can help us be more efficient there.
Oh, yeah, power. That's the rate at which energy is used, right?
You got it. So a high-powered appliance will use more energy in a given amount of time than a low-powered one.
Okay, so choosing energy-efficient appliances is a smart move.
Absolutely. And keep an eye out for those Energy Star labels. They indicate that a product meets certain energy efficiency standards.
I always wondered what those meant. Good to know. But it's not just about the appliances themselves, it's how we use them too, right?
You're right. We've all heard about phantom loads, those devices that keep sucking energy even when they're turned off.
Oh yeah, like leaving your phone charger plugged in.
Exactly. Unplugging chargers, turning off lights, and using power strips can really make a difference in your overall energy consumption.
It's all about being aware of where that energy is going.
And making conscious choices about how we use it.
This is making me think bigger now. Like, beyond our homes, what about the global energy challenges we're facing? Can understanding work and energy help us there too?
Absolutely. Understanding energy transformations is essential for developing and using renewable energy sources.
Okay, so like solar panels and wind turbines.
Exactly. Solar panels capture light energy from the sun and convert it into electrical energy.
Wow, that's amazing. It's like we're harnessing the power of the sun.
We are. And wind turbines capture the kinetic energy of the wind and transform it into electricity.
It's like we're using nature's energy to power our world.
That's the beauty of renewable energy.
But there must be some challenges too, right? It can't all be easy.
Oh, of course there are challenges. One of the big ones is energy storage. The sun doesn't always shine and the wind doesn't always blow. So we need efficient ways to store the energy we generate from these sources for when we need it.
That makes sense. It's like having a backup battery for when the renewables aren't available.
Exactly. Energy storage is a key piece of the puzzle.
Well, this has been an incredible journey. We've gone from basic definitions to mind-blowing concepts to practical applications and global challenges.
It's amazing how far we've come.
I feel like we've uncovered a whole new way of looking at the world.
That's what we hope for with these deep dives.
To spark curiosity and make you see things in a different light.
And to empower you to keep learning and exploring on your own.
Exactly. So thank you all for joining us on this deep dive into work and energy. I hope you've enjoyed it as much as we have. We'll see you next time for another fascinating exploration.